Einstein's explanation of the photoelectric effect presented a new challenge to scientists. Up until this time, they had explained the properties of light in terms of waves. Suddenly, it seemed that light could also behave like particles. How could this be? The resolution to this seeming paradox had to wait for three of the giants of 20th century physics, Feynman, Schwinger and Tominaga. Working independently throughout the 1940s, they discovered a quantum theory of light, quantum electrodynamics, or QED. Where Einstein had explained the photoelectric effect in terms of particles, Feynman and his contemporaries went even further. With quantum electrodynamics, they provided a mathematical way to explain all the wave behaviour of light in terms of particles. QED was a major milestone in our understanding of nature.
I think Feynman referred to QED as the jewel of physics. Probably not because he invented it, but it explains all of physics outside the nucleus and excepting gravity. Okay, so it is a theory that explains the interactions of matter particles with one another via the electromagnetic force, and that drives all of physics and chemistry and material science. And so it's a theory of almost everything.
As well as explaining the behaviour of light, QED provided a revolutionary way to look at forces. Instead of thinking in terms of force fields, as Newton and Maxwell had done, QED explained the electromagnetic force in terms of particles. To understand how it works, imagine two electrons approaching each other. We know that they'll move apart because like charges repel. QED says that the repulsion is caused by a photon, a particle of light, being transferred between the two electrons. So the photon is the particle that carries the electromagnetic force. QED proved so successful that it seemed natural to look for quantum theories of the other forces that concern us as particle physicists, the weak and strong nuclear forces. By the mid-1970s, theorists had predicted that the strong force required 8 exchange particles, called gluons, and the weak force required 3, the W+, the W-, and the Z. The problem was that these were just mathematical predictions, and as with everything else in science, if you want to be really sure about something, you have to see it. And to see it, you need one of these, a particle accelerator.